Hello, welcome back to the first course in general physics and to the subject thermodynamics. We are still in the topic of dealing with the thermodynamics of an ideal gas. And in this lecture, we will continue discussing the problem of the thermodynamics of ideal gas, and we will deal with the adiabatic expansion of an ideal gas, find the formula which relates the different state variables of the ideal gas in an adiabatic process. And then we will talk about the equation which relates the different variables in the case of a free expansion of an ideal gas. After we have finished talking about ideal gas equation and its thermodynamics, we will move to a new topic talking about the entropy as a new concept and a new quantity, and then start with the second law of thermodynamics, which we will derive from the basic principles, and then we will be coming to the end of this lecture. As a continuation for the discussion of our ideal gas, we would like to consider the adiabatic expansion of an ideal gas, since we have all the elements of knowledge that are required for dealing with such a problem. And now we recall that for an adiabatic process, the heat Q is equal to 0, in which case the infinitesimal change in internal energy of the system, dE internal, is equal to minus dW, the work done during this infinitesimal process. Now we can substitute for each quantity, recalling that E internal is simply NCVT. That's dE internal is equal to NC sub V times dt, because N and CV are constant. And this would be equal to minus the work, which is P dV, and we replace P by nRT over V from the state equation, the equation of state of the ideal gas. nRT over V, that's P, that's instead of P. And then we have this equation. We make this substitution in order to have the right variables which are necessary for performing the integration at a later stage. And then we rearrange these terms, move them to one side of the equal sign in the equation, and we divide the equation all by N CV T. We divide the equation by N CV T, and we get the final form of the equation, dt over T plus R over CV times dV over V is equal to 0. Now this equation is simple to evaluate by simply integrating over. And if we perform the integral, we will get the result in a simple manner. But before we do that, we have a constant that is involved, and we have to evaluate that constant. We recall that this constant R over CV is equal to Cp minus Cv over Cv. Recall that R is simply Cp minus Cv. We will use quantities that are only the molar specific heats of the gas. So we will get R over Cv is simply equals to Cp over Cv minus 1. And the ratio of the molar specific heats of the ideal gas, Cp over Cv, we call it gamma. So then we get R over Cv is equal to gamma minus 1, where gamma is the ratio of the specific heats. Then we replace R over Cv from in the previous equation with this quantity, gamma minus 1, and we do the integral. When we do the integral, remember that dt over t, it gives you ln t, and dv by v, the integral of dv over v gives you ln v, and thus we will have the result if we combine ln t and ln v, but ln v is multiplied by the factor Cp R over Cv, which is simply gamma minus 1. So gamma minus 1 times ln v, it is simply ln v to the power gamma minus 1, and we combine this ln t plus ln v to the power gamma minus 1, we get the result ln v ln t times v to the power gamma minus 1, and that is equal to a constant. This is the result of integrating that equation. And if we take the exponential of both sides of this equation, the exponential of the left-hand side is simply t times v to the power gamma minus 1, and the exponential of a constant is another constant, and we get the relation between these state variables of the ideal gas through an adiabatic expansion of the ideal gas in the form t multiplied by v to the power gamma minus 1 is equal to a constant, where gamma is the ratio Cp over Cv. And this is true for an adiabatic expansion of an ideal gas. Now, if we replace T by the value of P and V using the equation of state, or the equation of the ideal gas, namely PV equals nRT, if we replace T in that sense, we will get another form of this equation which relates state variables of the gas, namely P times V to the power gamma is equal to a constant. This is an alternative relation which is relating the state variables of the ideal gas in an adiabatic process. So thus we have these relations which relate the state variables. Each relation actually connects two variables, and the equation of state PV equals nRT for an ideal gas gives us the means to evaluate the third state variable by substituting into this equation. Now the question is, PV to the power gamma is equal to a constant which is a relation for the adiabatic expansion of an ideal gas. The free expansion of an ideal gas is adiabatic. The heat during the free expansion of a gas is adiabatic. Now the question is, does this ratio hold also for the free expansion of an ideal gas? PV to the power gamma equals to a constant. The answer is no, because it's not simply an adiabatic, and there is no path on the PV curve as we have derived in this equation, in reaching this equation. We have also the work done is 0 and the internal energy is 0. And since the internal energy for a free expansion of the gas, since the internal energy is fixed, that means the temperature of the gas during the expansion is constant. T initial is equal to a T final. So we use the ideal gas equation. We don't need to do any sorts of integral or integration because we don't have a PV path actually to integrate over in switching from state 1 to state 2. We just use the equation of state directly, and we know the initial and final temperatures are the same. So using the equation of state, we obtain the relation PV is equal to a constant for the free expansion, which is also adiabatic, but adiabatic and an adiabatic expansion that is not in thermal equilibrium at each stage of the transformation from initial state to a final state. It was not in thermal equilibrium. The system was not in thermal equilibrium, and no PV diagram was constructed for such a system. Thus, conclusion, for an adiabatic expansion of an ideal gas, the relation between the state variables is given by PV to the power gamma is equal to a constant, and the other variable T can be obtained either from the other relation TV to the power gamma minus 1 equals to a constant, or from the equation of state PV equals nRT. This is the relation that's true for adiabatic expansion of a free of an ideal gas. However, the relation for the free expansion is given by PV is equal to a constant, PV to the power 1, not to the power gamma. This is this concludes the talking about the discussion of the thermodynamics of ideal gases for the time being. And now we would like to move to another topic, which is the discussion of some principles of thermodynamics, discussing a new quantity of thermodynamics that describes states of thermodynamic systems, and then arrive at the second law of thermodynamics and see how it applies later on. In the beginning, we would like to emphasize that some processes that can occur in a closed system are irreversible. They just go in one direction, and that directional preference for some processes is independent of the fact that the process obeys the law of the conservation of energy. In mechanical processes, for example, the conservation of energy dictates the direction of the process. That's what happens in mechanical systems. But in thermodynamic systems, the conservation of energy is not enough to dictate the direction of a process. Let's give some examples. For example, if you hold in your hand a cup of hot tea, then heat will transfer from the cup into your hand. But you can never see the opposite. You can never see that heat will flow from your cold hand to the hot teacup. So when these two bodies come into intimate contact and interact by exchanging heat, heat will flow only in one direction. It will never flow in the opposite direction. Although in both cases, energy conservation is obeyed, whether you transform energy of the value Q from object A to object B or from object B to object A, it doesn't matter as far as energy conservation is concerned. However, the transfer of energy from the hot object, from the cold object to the hot object will never be observed. That's a directional preference. Another example is that if an object is rolling on a surface and it comes to a stop at a later point because of the transformation of mechanical energy into heat, you can never observe the reverse process. You can never see a stationary object that extracts heat from the environment and starts moving. You will never see that process happening in nature. That is also a directed process, although in both cases, those two, in this case also, the energy is conserved because you can extract heat of an amount Q and keep going, transform it into mechanical energy. But it never happens. You can always transform the mechanical energy of the moving object into heat, but not the other way around. So in spite of the fact that energy conservation is obeyed, certain processes can never happen in a certain direction. So direction of a process must be dictated by another quantity, not the energy of the system. What is this quantity that dictates the directions of certain processes and that does not allow the process, a certain process to occur while allowing another process to occur? This quantity is the so-called entropy. Entropy is a new quantity in physical quantity, and the direction of an irreversible process is not set by the conservation of energy. It's not, the direction is not dictated by the change in energy in that sense, but it is rather dictated by the change in this new property of the physical systems, which is the change in entropy. If we call the entropy S, then the change in this entropy, delta S, is what dictates in which direction does a given process in a thermodynamic system, closed system, in which direction does it occur. And this leads us to a postulate which is derived from the natural occurrence of processes and events. And this is the central property of entropy. This postulate is concerned with the central property of this new quantity, entropy, and it states that if an irreversible process occurs in a closed system, the entropy S of the system always increases. It never decreases. So when, for example, heat is transferred from a hot object to a colder object in contact with it, until the system comes to a thermal equilibrium, the system of the two bodies, that involves more randomness in the distribution of and the motion of matter within the two bodies, and that increase in randomness is associated with the increase of this variable, which is the entropy of the system. And thus, this direction, which goes from the transfer of energy, heat, from a hot object to a colder object in contact with it, is the natural direction that will take place, and it is associated with the change in entropy being positive, meaning the entropy increases through a thermodynamic process. It never decreases. But we have to remember that this is true for an irreversible process in a closed system. That is the condition, or these are the conditions for the application of this postulates. And now we conclude from this discussion that unlike energy, entropy is not conserved. In an irreversible process, the entropy always increases, it never decreases. That means entropy is not a conserved quantity. Entropy change tends to transform the universal matter into a more random matter in a way, and that transformation ensures the increase in entropy in the universe. The entropy is another state property of the system. It does not depend on how the system has arrived at that state. It is a state property, just like the internal energy, just like the temperature, just like the volume or the pressure of the system. It is a state-dependent quantity. It's another state-dependent quantity of the system. And now, the entropy change of a system can be defined in a mathematical form, and this is given by the mathematical definition delta S, which is the entropy in the final state minus the entropy in the initial state for the system, is simply the integral of the quantity dq over t. So at a given temperature, if we know the change in energy or the heat absorbed by the system at a given temperature, if we know the relation between the heat absorbed at a given temperature as a function of temperature in a way, we can integrate this quantity dq by dt by t, dq by t, and we can obtain the change in entropy of the system as it goes from an initial state to a final state. The units of entropy, as can be seen by the relation, it's units of energy per temperature, and the units of energy is joule. That's the units of Q. So the units of entropy is simply joule per per Kelvin. That is using the International System of Units. Now we consider the change in entropy for the free expansion of an ideal gas. The free expansion of ideal gas involves the expansion from one side of a container as we remove the stopcock to the other side, and as we can visualize the randomness of the distribution of the gas molecules in the larger volume is more. The randomness is more because there are more states in which the locations of the particles can occupy in the final state. More states available. That means there is more number of accessible states to the system, which means more randomness in the distribution of particles over this bigger space than as compared with the initially smaller space. And that more randomness will entail a larger degree of the entropy of the system. Now, if we are involved with this problem of evaluating what is the change in entropy for a free gas, for an ideal gas as it freely expands, if we want to use directly the definition for the entropy change, then we have a problem. Since we have no PV diagram, we have no PV path for the free expansion, as we mentioned. We don't have such a relation. We don't have such a relation between Q and T. So there is no way that we can evaluate the change in entropy for a freely expanding gas directly using the definition and using this process. So what do we do? The solution for this problem is the key point that the entropy is a state property of the system, which means it depends on the state and regardless of how we took the system into that state. Thus, knowing the initial state of the system, which is characterized by some S initial, and the final state of the system, which is characterized by S subfinal, then if we take the system from the initial condition or state to the final state via any other type of process, we will be able to evaluate delta S for a convenient process, and then that delta S as calculated for the new convenient process is the same as delta S for the freely expanding gas if we are careful about making sure that the initial state of our gas in our designed process is the same as the initial state in the freely expanding gas, and our final state is the same final state of the freely expanding gas. If we make sure that the initial states are the same and the final states are the same, so regardless of the fact that the two processes are different, delta S calculated is the same. So in that sense, we would choose a convenient process through which we can take the system from initial state to final state, and a process which is simple to evaluate the integral for dq by t. And that's what we are going to do. So we will replace our irreversible process, which is the free expansion of the gas, by a reversible process, because a reversible process, we can always plot a PV diagram for such a process. So we make this replacement in order to be able to solve the problem. And how do we do so? For example, we have this diagram which shows the gas before it expanded, held with a stopcock in one side of the container. And here, as we open the container, the stopcock, the gas rushes into the other side of the container, and we can see the more randomness of the distribution of matter, which involves the increase in entropy. We will replace this process by another process where we have a gas contained in a cylinder with a movable piston, a frictionless movable piston with shot lead on top of it, and we have this gas in intimate contact with a thermal reservoir, which we can adjust its temperature through the control knob of the temperature. So what do? Is we control the temperature of the gas using the knob, and then we control the pressure of the gas by removing or adding lead shot to it, and we make sure that we have the same amount of the gas that we had in the free expansion. That means, according to the equation of state, PV equals nRT, we will have the same volume of the gas in question. Thus, we make sure that this way we control our system to have exactly the same initial state of the freely expanding gas. And now what do? Is we fix the temperature, because through the expansion of the free expansion of gas, the temperature is constant, is fixed. So we fix the temperature, and we start expanding the gas by removing lead shot piece by piece, and the gas keeps expanding until it reaches the final state, which has a bigger volume. This is done at constant temperature, which means this is an isothermal process. So we replace our free expansion by an isothermal process. And why did we select an isothermal process? Because if we recall the definition for the change in entropy, the definition involves the integral dq divided by t. If the relation between dq and t is not known, then it's difficult to evaluate this integral. So we choose a process in which t is constant. In that sense, t will be moved outside the integral, and it is easy to evaluate the integral of the rest, which is q. Simply, the integral of dq is q, the heat absorbed by the system during the process, regardless of whether it is positive absorption or negative release of heat to the system. So this way, we replace our free expansion by a convenient process, and we are able to evaluate the change in entropy for the reversible process. The isothermal process ensures that T initial and T final are the same, which is equal to T, we call it, and thus delta S, which is simply the integral of dq by T, T is constant, it is equal to Q, the heat absorbed, over the temperature. This is the change of the entropy of the system as determined from the reversible isothermal process as the gas expands from the initial state to the final state. And in this process, because the energy the internal energy of the system is constant because the temperature is constant, that means the work done is equal to the heat absorbed according to the first law of thermodynamics. And since as the gas expands, the work done is positive by the system, that means the heat absorbed through the process by the system is also positive, which is equal to the amount of work done. So thus everything is fine. Delta S is equal to Q over T, and Q is positive, which means that delta S is positive. So it fits, this result fits the postulate, the central postulate of the entropy, which states that the entropy should increase. However, we have a problem. We have a puzzle. The puzzle says that we have a reversible process. The reversible process can either go in the direction where the gas expands isothermally, or it can go in the reverse direction, where we compress the gas from the final state to the initial state, back to the initial state, also isothermally. We can do that. And we should, in principle, get a zero change in entropy and a zero change in internal energy also, because we go back to the initial state. Now, in the first part of the reversible process of the cycle, as we expand the gas, delta S is positive. It is Q over T, and Q is positive, as we said. Then delta S is greater than 0, which fits with the postulate of entropy, that delta S should increase. It never decreases. However, in the reverse direction, if we compress the gas back to its initial state, we should have delta S is negative, which equals to the heat released to the system, because as the piston goes down, then the work done by the system is negative, which means the heat is released to the environment. The system cools down. The system releases heat to the environment, to the heat reservoir, and thus Q is negative, which gives delta S is equal to Q over T, which is a negative quantity. So this negative quantity is the same as the positive quantity that is obtained in the expansion case, which means that the total delta S is 0. Now, the total delta S is 0 is not okay, because the postulate says that delta S should increase. The entropy should increase. It never decreases. And in this case, in the total process, we have delta S is 0. It does not increase. Now, there is another part to the puzzle. It's not only that delta S is 0, which contradicts seemingly with the postulate of entropy. There's also, in this downward process, which is the compression, delta S is even negative. It decreases during that part of the process, which is a real trouble. Delta S should never decrease. So, what is the problem? The problem is that there is no problem, in fact, because the postulate of entropy stated that when we are dealing with an irreversible process in a closed system, we have these two conditions, and then the postulate is applicable. In our case of the gas, we have violated both conditions. For one thing, the process that we have used to calculate the entropy change is reversible. It's not irreversible. So that contradicts the condition. And the other thing is that the system, which is the gas, is not closed because it is in intimate contact with the thermal reservoir, where it can extract heat from the reservoir or release heat to the reservoir. So our system is not closed. So that means we should not really look into that postulate that we have mentioned, because neither the gas is closed nor the process is reversible. And in that sense, when we want to talk about a closed system, we will take into consideration the system consisting of our gas plus the reservoir. And if we take the system as the gas plus the reservoir, then as we go in the reverse process, which is the compression of the gas releases heat with the amount Q to the reservoir. So delta S for the gas as it is compressing is negative. However, the reservoir absorbs heat Q, which is positive for the reservoir. So if we take the total system together, the change in entropy for the gas is negative Q over T, and that for the reservoir is positive Q over T. So if we take delta S for the total system, delta S will be 0. And the same is in the case of expansion. In the case of expansion, delta S for the gas is positive, and delta S for the reservoir is negative because it loses an amount of heat Q. So its delta S is minus Q over T. That means the change in the entropy for the gas is equal and opposite in sign in both cases to the change in entropy of the reservoir. And that leads to the necessity for the modification of our postulate of entropy in order to take into consideration not only irreversible processes, but also to take into consideration reversible processes. And the modified entropy postulate reads, in a closed system, the entropy change increases for irreversible processes, and the entropy change remains constant for reversible processes, but the entropy never decreases. So this is the statement that is applicable to both reversible processes and irreversible processes. And at this point, I would like to end this lecture, and I thank you for your attention.